Now we are going to discuss about tensors. Now let us consider two coordinate systems. One is a Cartesian coordinate, which is x, y, z. So this is Cartesian coordinates in 3 dimensions. Now let us also consider another coordinate system 3 dimension, which is spherical polar coordinates, which is r, theta, phi. Now the Cartesian coordinate x is a function of r, theta, phi. Y is also a function of r, theta, phi. Z is also a function of r, theta, phi. Similarly, r can be expressed as a function of x, y, z. Theta is also a function of x, y, z. Phi is also a function of x, y, and z. Now we know the relation, the relation between the two coordinates. Suppose x is equal to r cos theta, r sin theta cos phi. So this is x, and you can also express y in terms of r theta phi, which is y is r sin theta sin phi, and z is equal to r cos theta. So x, y, z can be expressed in terms of r theta phi. Or we can also express r in terms of x, y, z. R is equal to, so by squaring and adding x square plus y square plus z square, and if we take the square root, we will get r. So r is a function of x, y, z, which is x square plus y square plus z square whole power half. Theta is the tan inverse of x square plus y square by z square whole power half, and phi can be expressed as tan inverse of y by x. So if you consider any two coordinate systems, one coordinate may be expressed in terms of the coordinates of the other system. So Cartesian coordinate may be expressed in terms of spherical polar coordinates. Spherical polar coordinate may be expressed in terms of the Cartesian coordinates. So this we are considering a specific 3-dimensional system. In general, suppose if we choose an n-dimensional system. In the n-dimensional system, let us consider two coordinates systems. The coordinates are x1, x2, x3, and xn. This 1 to the superscript x1, superscript x2, and x3 is this is a superscript xn. So there are n coordinates. Let us choose in one coordinate system. Let us similarly choose another coordinate systems in the same n-dimensional systems. Here we are using barred system. So in order to distinguish between the this system and this system, that is unbarred system. This is unbarred coordinate system. We can say this is a barred coordinate system, so that we can differentiate the two coordinate systems. So this is x1 bar, x2 bar, x3 bar, and xn bar. So x1, x2, x3, xn is a set of coordinates in one system. We call this is a unbarred coordinate system. x1 bar, x2 bar, x3 bar, and xn bar, another set of n coordinates in the barred coordinate systems. Now here also we can say the x1 bar. So the one of the coordinates in the barred system may be a function of the coordinates of the unbarred system. So x1 bar is a function of x1, x2, and xn. So for any kth coordinate, xk bar is a function of x1, x2, and xn. So equation 1 represents the any coordinate in the barred system may be expressed as a function of the unbarred coordinate system. Similarly, any coordinate of the unbarred system may be expressed as a function of the coordinates of the barred system. So x1 is a function of x1 bar, x2 bar, etc. up to xn bar. So the this x1, this is one of the coordinates in the unbound system is expressed in the is a function of the other coordinates in the bound system. So for any coordinate xk in the unbound system is a function of xk is a function of x1 bar, x2 bar and xn bar. So there are two equations, equation 1 and 2. So in equation 1, the bound coordinate, one of the coordinates in the bound system is expressed as a function of unbound coordinate system, and the equation 2 represents the one of the coordinates in the unbound system is a function of the coordinates of the bound systems. Now let us write down the coordinate transformations. Now, so for this, now differentiating this equation 1 and 2. So now let us differentiate equation 1. So this is a equation 1, and you differentiate 1. So partial, this is a dx alpha bar. So you differentiate one of the coordinate. Dx alpha bar may be expressed as summation over I runs from 1 to n, partial dx alpha bar by partial dxi dxi. There is a summation over I. So partial dx alpha bar by partial dx1 dx1 plus partial dx alpha bar by partial dx2 dx2 and so on up to partial dx alpha bar by partial dxn dxn. So since it is having n coordinates, and we will have the terms, there will be n terms. So this can be expressed as a summation over I runs from 1 to n. So similarly, if we take equation 2 and if you differentiate, you will find dxi, which is a summation summation runs from alpha is equal to 1 to n, partial dxi by partial dx alpha bar into dx alpha bar. Summation alpha runs from 1 to n. So here also you can have n terms because xi is a function of your n coordinates. So partial dx1 divided by partial dx1 bar into dx1 bar plus partial dxi divided by partial dx2 bar, dx2 bar, and etc. up to the term partial dxi divided by partial dxn bar into dxn bar. So that n terms can be expressed in terms of this expression, the summation runs from alpha is equal to 1 to n. So we have now your two expressions. Now here we are going to use Einstein's summation convention. The summation symbol may be removed from this expression according to this convention if two indices are repeated in this expression. So in this above expression, I is repeated. If there is a repeated index, that means summation is over I, which is from I is equal to 1 to n. So this summation sign is buried. So we can remove that summation sign in that expression. So in that expression, we remove that summation sign. And the meaning, if two indices, here also I, when two indices are repeated, then summation sign is buried. So similarly, dxi is equal to partial dxi by dx alpha bar into partial dx alpha bar. So in the expression for 3, the sigma sign, the summation sign, I runs from 1 to n as well as alpha runs from 1 to n may be removed. We may, according to the convention, the symbol is buried within the expression itself. So whenever two indices are repeated, we can call this is a dummy index. The dummy index runs from 1 to n. Now let us find dxi by dxj. Dxi by dxj. So you know dxi. Similarly, you find it dxj. You divide dxi by dxj. Here when I is equal to j, it is 1. Otherwise, if it is different, this will be 0. So this is called as a Kronecker delta symbol, delta ij. Similarly, dx alpha bar by dx beta bar is also delta alpha beta, means this is a Kronecker delta, alpha and beta are equal, this is 1, otherwise it is 0. So this 4 is the definition of Kronecker delta. Now let us, so this is Kronecker delta. Now let us go again to the equation 5. In equation 5, the dxi by dxj, dxi by here, this is a dxi by dxj. So you know, you have already defined a dxi and a dxj. Once if you substitute, you will get this expression, partial dxi by dx alpha bar and dx alpha bar by partial dx j. This is equal to delta ij, because this is defined as a Kronecker delta, delta ij. So there is a summation over alpha. So this is the definition for delta ij. You may also express this form also, partial dxi by dx alpha bar into partial dx alpha bar by partial dxj, because there is a summation over alpha. So this is reduced to the Kronecker delta. Similarly, the other coordinate system also, dx alpha bar divided by dx beta bar, you substitute for dx alpha bar and dx beta bar from equation 3. You can express this is partial dx alpha bar by partial dx k divided by dx beta bar, which is can be expressed as partial delta alpha beta. So equation 5 is that this the expression for Kronecker delta. Now let us consider n quantities. So A1, the superscript 1, 2, 3. They are not the power, they are only the script. A1, A2, An. Then a coordinate system. So let us consider n quantities. A1 is one quantity, A2 is one quantity, and A is the nth quantity. We consider n quantities in a coordinate system. In the coordinate, the coordinate system we are choosing is unbound coordinate system, x1, x2, xn. So in the unbound coordinate system, x1, x2 and xn, we consider the coordinates, we consider the some quantities a1, a2 and an. And similarly, let us consider another coordinate system. In the another coordinate system, this is a Baud system. In the Baud system, x1 bar, x2 bar and xn bar. So that in n dimension we will have n coordinates. So in that system, the quantities, you consider the quantities a1 bar, a2 bar and an bar. So a1 bar, a2 bar and an bar. So these are the n quantities in the Baud system. So we have two type of quantities. One quantities a1 to an are the expressed in terms of the expressed in the unbound coordinate system. Another n quantities a1 bar and etc. an bar are the n quantities in the Baud system. Now let us find the transformation relation between the these two quantities in the unbound system as well as a Baud system, and this is expressed by a alpha bar. So this is the one of the component in the Baud system. This may be expressed as partial dx alpha bar by partial dxi ai. So this ai is a quantity expressed in the unbound system. A alpha bar is so a alpha bar is the quantity. So this is the quantity expressed in the Baud system. So the quantity expressed in the Baud system and the quantity expressed in the unbound system is related by the expression partial dx alpha bar partial dxi. So this is one of the transformation relation. So equation 6 represents a type of transformation relation. If the type of transformation relation is of this form, then this ai as well as a alpha bar can be called as the contravariant vector or contravariant vector of rank 1, tensor of rank 1. So it can be called as a contravariant vector or contravariant tensor of rank 1. Contravariant tensor of rank 1 we call as a contravariant vector. So this is 6 is the definition for the contravariant vector or the contravariant tensor of rank 1. Now let us take expression 6, and if you multiply by partial dxk by dx alpha bar on both sides, and if you sum over alpha, because whenever the indexes are repeated, there is a summation over alpha. That is the meaning according to the Einstein summation convention. So if you sum over alpha, you will get this expression. So this expression, the partial dxk by dx alpha bar in the partial dx alpha bar with partial dx I is a Kronecker delta. So this is a Kronecker delta. So this is becomes like this. Now if you multiply by ai, and only when k is equal to I is a non-vanishing value, so your I may be replaced by k. So this is another expression. So if that expression a k, the k may be replaced by I for convenience. So just you replace the k by I, you will get ai is equal to here, and this expression becomes partial dx I divided by partial dx alpha bar into a alpha bar. So this is equation 7. So equation 6 and 7 both are the definition of a contravariant vector. So this is a contravariant vector. The barred system may be expressed in terms of the contravariant vector in the unbarred system. So this is 6 is a transformation relation. Equation 7 represents the contravariant vector in the unbarred system may be expressed in terms of the vector in the barred system. Now let us consider n quantities, a1, a2, a3, an in a coordinates system. The coordinate system is x1, x2, xn. So this unbarred coordinate system, we consider a1, a2, n some n quantities. Now similarly, we can choose another type of coordinate system, x1 bar, x2 bar and xn bar. This is another coordinate system. This is a barred system. This is a unbarred system. And a1, a2, an. So this represents the sum of the n quantities in this here. And this a1 bar, a2 bar, an bar, this represents some n quantities represented by this one. And if these two quantities, they are unbarred quantities, are related to the barred coordinates by the transformation. Suppose if a alpha bar is equal to partial dxi by partial dx alpha bar ai. So in previous case, the transformation is partial dx alpha bar by partial dxi. But here, if the transformation is of this form, partial dxi by partial dx alpha bar ai, then this ai is called as a covariant vector or covariant tensor of rank 1. So this is the equation 8a is the definition for the covariant vector. Now here also you multiply equation, this 8a. So this is you choose this is 8a, and if you multiply with partial dx alpha bar by partial dxk on both sides, and if you perform the summation over alpha, here if you perform the summation over alpha, this terms becomes delta ik, this becomes a Kronecker delta, and the whole term will be a non-vanishing value only when I is equal to k, so this becomes ak. So this is ak. Again for convenience we replace k by I, and ai is equal to partial dx alpha bar by partial dxi a alpha bar. So this is the expression. So 8a and 8b, here if the transformation, the quantities expressed in the unbarred system and the barred system are related by 8a or 8b, then these quantities can be called as a covariant vector of rank 1, covariant vector or covariant tensor of rank 1. So equation 8a and 8b are defined as the covariant vector or covariant tensor of rank 1. Now let us define covariant, contravariant and mixed tensor of rank 2. So next order, the first order is rank 1. Suppose the rank, the order is 0, this is a scalar. So order is 1, it is a vector. If it is order 2, now let us discuss. Now let for order 2, because there are two indices, I, J. I runs in n dimension, I runs from 1 to n, J runs from 1 to n. So the total number of quantities A, I, J will be n square quantities. A11, A12, A13 and so on, and A21, A23, A33 and so on up to AN. So you have n square quantities will get. Let us consider these n square quantities in a coordinate system. So you will have n square quantities. If is defined in a coordinate system, x1, x2 and xn. So this is a unbound coordinate system. Similarly, we consider another quantities, n square quantities. So again you consider another n square quantities, a alpha bar, a alpha beta bar. Here also a11 bar, a12 bar, a13 bar, etc. up to a n bar. So again you have n square quantities. So you consider n square quantities in a coordinate system as well as n square quantities in the other barred coordinate system. So the barred coordinate system is the quantities here, x1 bar, x2 bar and xn bar. So now let us consider these two coordinates, and the transformation is of this form. A alpha beta bar is equal to partial dx alpha bar by partial dxi, partial dx beta bar by partial dxj in the Aij. So this is expressed by equation 9. If the transformation between the two quantities, one is expressed in the unbarred system, another quantity is expressed in the barred system. So this is a barred system, this is unbarred system. The two quantities are related by this type of transformation. The transformation, this is the transformation. So this is the transformation. Then this is a, we can call this is a contravariant tensor of rank 2. So whenever the indices, the contravariant vector or contravariant tensor, the indices must be in the superscript. Now similarly we define a covariant components of a tensor of rank 2. So in covariant tensor, the transformation relation is different. Now so let us take the expression 10. Sorry, equation 10. A alpha beta bar, here, yes, A alpha beta bar is equal to partial dxi by partial dx alpha bar, partial dxj by dx beta bar Aij. This is equation 10. Yeah. So this is equation 10. So this is a transformation is of this form. If the transformation is of this form, according to the equation 10, then this Aij as well as A alpha beta bar can be called as the covariant components of the tensor of rank 2. So covariant tensor of rank 2 is satisfied by this transformation relation. So the transformation relation tells you about whether the components are, or the quantities are contravariant or covariant. So according to this, if it satisfies equation 10, it is a covariant tensor. If it satisfies equation 9, it is a contravariant tensor. Also we may define Aij. So one superscript and one is a subscript. So this is Aij as a, so this is components of a mixed tensor of rank 2. So one contravariant rank. One indices is present in the superscript. It's a contravariant rank 1. One index in the subscript. So this is a covariant rank 1. Total rank is 2. 1 plus 1, 2. So this is defined by A alpha beta bar A alpha beta bar is equal to, so the one alpha is in the superscript and beta is in the subscript. Then according to the equation 11, if it satisfies equation 11, that is A alpha beta bar is equal to partial dx alpha bar by partial dxi and partial dxj by partial dx bar. So the transformation of this form, and this Aij is related to A alpha beta bar according to the equation 11. We can say this is a mixed tensor of rank 2. The total number of indices represents the rank, total rank, and of the subscript 1, there is a superscript 1. So this is rank 1 and this is rank 1. So total rank is 2. So using this definition, the tensor of higher rank can be defined. Suppose alpha 1, alpha 2, alpha p. There are p index in the p indices in the superscript here, and q indices in the subscript. So what is total number indices? P plus q. So the tensor has, the rank is p plus q. So this is defined by because this is a mixed tensor. So partial dx alpha 1 bar divided by partial dx1, partial dx alpha 2 bar divided by partial dx2, and so on up to partial dx alpha p bar divided by partial dx ip. Then partial dx j1 divided by partial dx beta 1 bar, dx j2 divided by partial dx beta 2 bar, and so on up to partial dx jq divided by partial dx beta q bar. A here the superscript I1 I2 up to ip, j1 j2 up to jq. So equation 12. So equation 12 represents the transformation relation between the tensor whose contravariant rank is p and covariant rank is q, and the total number of components is n power the rank p plus q. N power p plus q is the total number of components. So this is the total number of components. So using this definition, we can show that the velocity and accelerations are contravariant tensor. Now here, and now let us choose one coordinate system. This is a bar coordinate system. So here x alpha bar is equal to x alpha bar is a function of x1, x2, xn. So any component in the bar system may be expressed in terms of the quantity and bar system. Dx alpha bar is partial dx alpha bar by partial dxi into dxi, that is a summation over I. So I runs from 1 to n because the n dimensional system. If t denotes the time, now dividing the above expression, so here dx alpha bar by dt is equal to partial dx alpha bar by partial dxi, the dxi by dt. So if we define dx alpha bar by dt, so dx by dt, this is a velocity. So velocity expressed in the bar system, and this is the velocity expressed in the unbarred system. And if we substitute back here that expression, v alpha bar is equal to partial dx alpha bar by partial dx I into vi. So from this expression, from this transformation, you look at the transformation, the transformation suggests you that Vi and V alpha bar, they are the contravariant vector. So you just check the transformation. From the transformation relation tells you whether the components are contravariant or covariant. Now you take the time derivative. Again you take the expression in 1, and you take the time derivative of expression 1. dV alpha by dt, which is partial dx alpha bar by partial dx in the dvi by dt, and if you, this is the rate of change of velocity, so this is acceleration. So you a alpha bar is equal to partial dx alpha bar with partial dxi. So again the transformation relation tells you that these components are ai and ia alpha bar are the contravariant vector. So from equation 1 and 2 we see that acceleration as well as the velocity. So equation 1 tells you that velocity is a contravariant vector. Equation 2 tells you that acceleration is also a contravariant vector. So the transformation relation is important. The transformation relation tells you about whether the components are contravariant or covariant. Now let us choose one simple example. Suppose you are having a quantity A, this is A, which is a function of I, J, K, I, J, K, L. So this is your I, J, K, L, which is a function of coordinates. So this A is a function of the coordinate, which is transformed to another coordinate. So this is another bar coordinate system, A alpha bar. This is a bar coordinate system, A alpha bar, which is the function of alpha, beta, gamma and delta. So we have this 4-dimensional system, you can say. So there are one component in the unbarred system, this is a component in the barred system. Now the transformation relation between the unbarred and the barred coordinate as well as the unbarred coordinate system is given like this. So the transformation relation is given like this. So from this you can find the type of the vector. So here I, K, L, the bar coordinates are alpha, beta and delta. So whenever this side is a bar and this is an unbarred system, according to the definition, if barred coordinate is in the denominator, then this here the index must be alpha. So here this must be alpha, beta, delta, because alpha here, beta here, delta here are in the denominator. So here it must be also in the subscript, and gamma is in the numerator part. So here it will be a superscript. So this A bar, which is a function of alpha, beta, gamma, delta, must be of this form: A bar of gamma, alpha, beta, delta. And similarly A, I, J, K, L must be A, I, J, K. So this is the. So this from this transformation, the transformation relation suggests to you that A must be of this form, and A bar here must be also the form mentioned here. So from the transformation relation is important. From the transformation relation only we can get a conclusion about the components, whether it is contravariant or covariant or mixed tensor.